All right, my name is Ben Titzer, and I'm delighted to present this paper at ASPLOS. So this is joint work with Heather Miller and our students, and the title is Flexible Non-Intrusive Dynamic Instrumentation for WebAssembly. So the motivation is the first sentence of our paper. Programs have bugs and sometimes run slow. Now, there are many techniques that we can use in the static analysis world to help us with bugs, like type checking, linting, and verification. But there are also tools in the dynamic world, in particular, tracing sanitizers, leak detectors, and also debuggers. This running slow part is actually very important. I'm very interested in that. And tools for that include profiling, code coverage, cache simulation, and things like that. This paper is all about dynamic analysis for WebAssembly, and we are doing this in the context of Wizard, which is a system that we've been developing for the past couple of years. And this is a WebAssembly engine designed specifically for research, in particular observability. Some insights that we have about program analysis are that, in particular, program analyses are tied to specific locations oftentimes. They're very sparse in time, and they have varied logic other than that. So we need a programmable mechanism. In particular, some examples of this are code coverage, branch profiling, memory profiling, dynamic call graph construction, of course, debuggers, and fuzzing. And Wizard has basically got many mechanisms, but one of them that specifically supports this use case is callbacks. Of course, we don't call them callbacks, we call them probes. That's the parlance that we use in the paper. And the idea is that Wizard has a bytecode interpreter, so it also has a JIT, but the idea with the interpreter is that it's very easy to support callbacks. In particular, you can get a callback when you're in the middle of execution, and this user level callback executes in the state space of the engine. So it doesn't execute in the state space of the WASM code, so it can't modify the WASM state inadvertently. If it wants to get the WASM state, we have an accessor for that. So there's basically a facade that separates the callback from what the WASM program state is, including the memory, execution stack, the value stack, and so on. So it's controlled here. There's a pinch point in the API. So if you think about the interpreter, it's kind of easy to get an interpreter to give you callbacks. In particular, getting a callback for every bytecode, we call that a global probe. So you insert a global probe to get a callback for every bytecode that's executed. And implementing that in the interpreter, a key point is that you don't want to slow down programs when they're not being observed with global probes. And the technique that we developed here is to use a dispatch table register where the normal dispatch table, which contains logic for every bytecode, can be swapped out by changing a single register to point to a dispatch table that calls user callbacks and then does dispatch. And that's great because we can turn it off again. So in particular, if we are done with our global probes and done with our analysis, we can switch back to the normal dispatch table. Of course, most analyses don't need a callback for every single instruction, so we also support callbacks called local probes that are tied to a specific location in the program. And that's going back to the insight that most analyses are actually sparse. So there's a point of interest, and we can insert a probe at that point of interest, and this is implemented by making a copy of the original code and modifying it by actually overriding that byte. This will cause the interpreter to trip over that invalid bytecode, and then it will be able to figure out that it should call the user callback. And as before, that callback will get a handle to all the state, and it can do its work. And then after the work is done, we can figure out what was the original byte by going to the original code. It's at the same offset. This also supports removing. So we can just copy the byte back. And so all these operations mean that there's no overhead in the interpreter for executing regular instructions, and we can insert and remove at a small constant time cost. Of course, probes are the mechanism, the building block for complex analyses. And in particular, this ability to remove them can be used to implement things like code coverage. So one way to do that is to insert probes at the beginning of every basic block in the program. And then we are going to keep state that keeps track of whether the block has been executed. So as the program starts running, the first probe executes, we record that the block has been executed. But since we only need to record that once, we can remove the probe. And so that probe will not fire again. And then as the program executes more control flow, the probes in those basic blocks are going to fire. We're going to record that those basic blocks have been executed, and they're going to remove themselves. And eventually the program is going to be free of probes in all of the paths that it executed. And the program might actually be hot and eventually be compiled by a JIT compiler. And so the hot code is going to asymptotically approach no overhead. So this is one of the really neat things about being able to remove probes is that you can signal to the engine that you're done with this code. So probes are what we build lots of dynamic analyses out of. In particular, we can build loop profiling, branch profiling, code covering, as I showed. All the tracing modes of the engine, including all the things that dump out stuff as it executes. There's only one mechanism in the engine itself, and that's probes. And so that keeps the separation between the analyses and the engine clean, and it means that there's a clear contract. So we implemented lots of things. In particular, we implemented a whole debugger REPL, and all of it just used probes underneath. So this is great. So we get observability. We can do lots of programmable things. What's the overhead like? And so this experiment compares bytecode rewriting, so injecting bytecode into a WASM program to record the direction of all branches versus using a monitor, which has probes in Wizard. And the answer is that it's lower overhead. So the interpreter doesn't have to execute as many instructions as it would with bytecode injection. And so instead of a 2x, it's more like a 15% overhead for the branch monitor and the interpreter. But the problem with that is that this is an interpreter. Interpreters are much slower than compiled code. In particular, they can be up to 30 times slower than compiled code. So what's the real overhead here? So we slow down a slow system by only a little bit. So this is not really transferable. So we really have to do this in a system that has a JIT. And so that's one of the things that we've been working on for the past year and a half or so is to build a JIT for Wizard that's competitive with the state-of-the-art single pass compilers. And this supports instrumentation with local probes as well. And so the idea is that we can compile direct calls into the instrumentation. One of the key design ideas is to use the same stack frame layout as the interpreter. And so that stack frame looks like this. I won't be able to explain everything here, but every execution frame is the same size, and the values for the WASM program are in the same locations. And so that makes it very easy to switch between the two, and also makes it very easy to look into the stack to satisfy some kind of request to look at state. So that gives us fast switching and also easy observability. Normally, the interpreter will tier up to the JIT when it encounters hot loops and also hot functions. Under normal circumstances, if we don't have probes running, there's no need to go back to the interpreter because this compiler does not do speculative optimizations. However, if we insert new probes into the code, then we might actually have to go back to the interpreter. And also, if we change something in the JIT compiled frame, it might invalidate some assumptions. So we'll see that in a minute. Baseline compilation basically works by doing a single pass over the code from the start to the finish. And since the bytecode is a source of truth, a probe will appear as an invalid bytecode when the compiler is running through the bytecode. And so it's easy to see that when we hit that bytecode, we just compile in a runtime call to instrumentation. We don't even need to know what probe it is, just where it is, so we can do a lookup. But the thing is that many probes are actually very simple, like counters, for example. So we implemented optimizations, what we should call JIT intrinsification of probes for certain types of probes that are very common, like counters. So in particular, instead of compiling a call into the runtime that's going to do a lot of work that eventually results in just incrementing a counter, we can just increment the counter directly in machine code emitted by the JIT, which is just 2 instructions. Other kinds of probes might do similar simple things, and they really just want a little bit of state. In particular, the branch profiling monitor really just needs to know what is the value that is going to be the input to the branch, which is on the top of the stack. So we also support intrinsifying probes that do limited things with state and just read them like the top of the stack. So in this case, the JIT will just emit calls directly to the user function and pass the stack top and not mess around with any of this frame state accessor. It's really important that there's a consistency model. Now we've got an interpreter and a compiler in the mix, and we want to do dynamic probe insertion and removal. That should really have the same effect no matter what is going on behind the scenes. And again, we saw some examples of that, like code coverage but also debugger actions, like if we insert probes in order to accomplish step instruction or step over, or we're doing other things, we really want all that to work. And so we don't want the JIT to ruin our analysis just by trying to make things faster. So the consistency guarantees are really required for the system be usable. In particular, what order do the probes fire in? If you insert multiple probes on the same instruction, they should really fire in a consistent order. If you remove them, they should also fire in the same order, no matter what tier you're running in. And obviously, if you change a value in a frame, it should take effect pretty much immediately. So the sort of goal here is to make the system kind of seem like it's just an interpreter, even though it's got a compiler in the background. So in the JIT, that basically means that we need to do something and reuse a mechanism that's been known for years called de-optimization. That's been used for speculative optimizations. So we use the bytecode as the source of truth for where the probes are. And so if we insert a new probe, then we have to invalidate this machine code. It's not right anymore. In particular, it needs to be re-instrumented. So that's what we do. So any executing frames that are in the old code, they will go back to the interpreter, and anything that calls into this code will go into the interpreter. We just rely on the interpreter to, again, warm up the code. And so if the code gets hot again, it will get recompiled. So it's very easy to just go back to the interpreter and everything will pretty much just work. So there's lots of performance results in the paper. We compared to many different systems. I don't really have time to do that justice in the remaining minute or so. So I'll just mention intrinsification makes a huge difference for certain types of applications. In particular, this hotness monitor, this basically counts every single instruction. If you do that, it's like 100x overhead. But with intrinsification, it goes down to something like 8 or 9x. So that's more reasonable. The branch monitor, if we have no intrinsification, the overhead is something like 10x, and that goes down to something like 2x with intrinsification. So that's a big deal. It basically means that the branch monitor is even though it's not built in and is a programmable thing, it gets pretty much as good performance as you can hope for. And the reason for that reduction is basically we broke that down into the amount of time that you spent going between the compiled code and the instrumentation, and also the instrumentation itself. And so now we're actually eliminating most of the overhead here. So you can see this dark red is the actual program. So we're getting pretty close to the actual program's execution. And that's about all I got time for. So thank you, and please see the paper for details.